Okay, I have to pencil back in and add it in. Okay, now I should be able to write. Okay. All right, so this theorem goes way back to Euclid, about 2,500 years ago, maybe 230 before the Common Era. It says, okay, so how do you prove that there's an infinite number? Well, you can't count all of them and just by counting show that it's infinite. So you assume the opposite and get a contradiction. So suppose there's only a finite number of primes. Okay, so suppose we have this finite number of primes, 2, 3, 5, 7, up to p, and p is the last prime, no more primes. Let's form one more than the product. And we can do this because we're forming a product of a finite number of numbers, and you can do that. There's a part of analysis called infinite processes, in which you deal with products, with infinite products, that is, products of an infinite number of factors, just as you've already, to some extent, dealt with the sum of an infinite number of terms. But here there's no problem. By closure, we have a finite number of factors, 2 through p. So n equals 2, 3, etc., up to p plus one more. Okay, so we're supposing that there's not an infinite number. Suppose there's only a finite number, and let's get a contradiction. Well, first of all, okay, I trust you all hearing me, right?
Yes, Professor.
Good, thank you. Thanks for the confirmation. Thanks for the confirmation. Never quite sure with this. Okay. Look, if this number capital N is a prime, it's certainly bigger than any of the primes we have listed. So, right, I mean, go back to greater than. For instance, take the 2 there. Well, as soon as it's multiplied by 3, forget about all the other things. You already have a bigger number by the definition of greater than. But okay, I don't have to belabor that point. It's clear that 2 times 3 times ... times p plus 1 is going to be bigger than any one of those factors, and then you're adding 1 to it. Okay, so n is bigger. And well, if n is a prime, then you have a larger prime than any that you listed. So that was wrong. That wasn't all the primes. There were more primes. So that's a contradiction. But if n is not a prime, then from the theorem we had, the first theorem Tuesday, it has a prime factor. Let's call it P star. So notice how it builds up. I mean, this isn't necessarily how all of mathematics was developed. Mathematics was developed partly chaotically, where people get an insight and they jot something down, and then other people sort of fill in the details. And by the time you see it in a textbook or in a class, everything is neat and worked out and runs smoothly and logically. So it kind of gets fixed up, so to speak. And so, I mean, that's what's happening here. Each time we've proven something, we go ahead and usually, if not always, eventually use it again. So if we have all the primes, and that's what we're supposing at the top, suppose not, suppose there's only a finite number of primes, or the only primes, then, of course, this P star is one of those primes. And therefore, a factor of that product. So you mean by factor, it's one of the numbers that gets multiplied. So P star is a factor of n and the product. And now instead of that, I'm going to subtract the product from both sides and get n minus the product equals 1. And so since n is a factor, since P star is a factor of n, and it's a factor of this term, it's a common factor. Of the left side. And now we go back to our definition of being a divisor. What does it mean to say P star divides 1? It means P star times something is 1.
So it cannot be prime, right?
Right. I'm just looking where I should close these parentheses that I started after those arrows. P star is a common factor of the left side. I guess over here. Yeah, right. But P star being a prime is not 1. And from the lemma at the beginning of the last class, yeah, P star, a divisor, a supposed divisor of 1 would have to be less than or equal to what it's dividing into. It's not 1, and 1 being the smallest positive integer. So that means is not less than, right? I cross out the is less than sign. Contradiction. Why? Because P star of prime would have to divide 1, and as we just saw, so we've arrived at a contradiction So from the first theorem that we had on Tuesday, over here, if n is not a prime, then from the first theorem of the last class, n has a prime factor. Whoops, sometimes the screen moves and, okay. So the prime factor of n, which is p star, so by this theorem from Tuesday, n does have a prime factor, p star, but we just found out that assuming that p star was one of the supposedly finite number of primes, 2, 3, 5, 7 up to p, well, if it's one of those, we got a contradiction, and so the prime factor of n, which is p star, it is a prime by Tuesday's theorem, must be a different prime from the 2, 3, up to prime, up to p, to prime p. And so and this is the idea of proving that a set is infinite. Whenever, I'll put it informally, whenever you think you have all the primes you don't, there are always more than any finite number. This is the idea of infinity. And if there can't be a finite number of them, of whatever they are, in this case primes, the number of primes, or of whatever you're counting, in this case primes, is infinite. And let me say that again, because that's an important idea when you're dealing with infinity. A set is infinite if for any number of them, and infinity isn't a number. So for any finite number, but when I say number, it means a finite number. So when you have any number of them, any finite number of them, whatever the things are of any set, in this case, a set of primes, you show that the assumption that you have all of them is erroneous. You get a contradiction, which means you don't have all of them. So what that says is for any finite number of them, there's always one more. Some people sort of confuse that with saying there's always one more. But if you speak of the set itself, let's take the set of primes, or let's take a simpler one that you're more familiar with, the set of all natural numbers, 1, 2, 3, 4, 5, and so on. Why is that an infinite set? Well, because if you stop at any finite number of them, there's always another one, such as one more than wherever you stopped. So if you think that you have n natural numbers, no, n plus 1 by the closure property is also in the set of natural numbers. So at any finite stopping point, there's always another one. Don't confuse that with saying the set of natural numbers. Once you've said the entire set of natural numbers, by the definition of the word entire, there aren't any more. But it's already an infinite set. So let's just take a look at a little corollary. So corollary, we've discussed this before. A lemma is a preliminary theorem that's used to sort of break up a complicated, longer main theorem, and a corollary is also a theorem. So a lemma and a corollary, they're both theorems. They're both true statements, but the idea of a corollary is that it follows in some sense easily from the main theorem. So So as I was saying, I said before, and I just said it a few minutes ago, the distribution of primes is very erratic and unpredictable, and there's no formula that tells you even one more prime after a given prime. But we can say that if, let's say, p sub 1, p sub 2, up to, say, p sub r, or I could have used 2, 3, 5, 7, it doesn't matter, up to p sub r are the first r primes, then there must be a prime number which could be the next prime after p sub r. In the interval p sub r plus 1 and p sub 1, p sub 2, up to p sub r plus 1. Now, why is this just a corollary? What's that? Okay, so Okay, well, if that product plus 1 is itself already a prime, then it's within the interval ending with that. If not, all right, so as we said, quoting the first theorem from Tuesday, it has a prime factor and the prime factor from the lemma at the beginning of Tuesday's class has to be less than that product plus 1. That is, if it's not a prime number, then it can be factored. It's a composite number. It can be factored, and according to the lemma from Tuesday, that factor has to be, well, it can't equal that because we're saying that's not a prime. If not, then it has a prime factor which is less than that product plus 1. But as in the theorem, it is not. Why is this screen jumping? It is not one of the primes p sub 1 through p sub r. It must be more than p sub r. In other words, it has to be at least p sub r plus 1. So, yeah, in the interval, starting with p sub r plus 1 and going up to that product plus 1 inclusive, it could be as small as p sub r plus 1, or it could be as big as this product plus 1. So you do catch the next prime in that interval. Now, of course, I'm not saying that's the only prime. It probably isn't, but there is a prime there.
Professor.
Yeah.
Wouldn't it be impossible for it to be p sub r plus 1 because all primes after 2 are odd, so p sub r plus 1 would be even?
Yeah, so it couldn't be exactly, yeah, so at least, yeah, so actually it would have to be more than that. But if you take a look at the interval, just the largest possible interval, but yeah, it could not be p sub r plus, good point, it couldn't be p sub r plus 1, but it will be, I mean, so I could say in the interval, I guess p sub r plus 2 up to the product plus 1 inclusive. This isn't wrong, but yeah, okay, so there's one number there that, yes, indeed, could be left out. Okay, very good, very sharp to notice that. So this isn't wrong, it's just, I don't know, easier to say that if it's bigger than p sub r, it has to be at least p sub r plus 1. But in fact, yes, for primes, it would not be exactly p sub r plus 1. Now, there are, as I've said before, there are many unanswered questions about primes. Let's take a look at some things that are unknown. about the distribution of primes, where they appear. Again, it's so irregular that there's no way, there's no formula, there's no way of predicting even one more prime, much less all of them, even if you already have a prime. We've looked at this before. Is there an infinite number why is this jumping around? Is there an infinite number of twin primes or paired primes that except the only even prime are as close as primes can be. Which would be consecutive odd numbers. So is there an infinite number of twin primes, paired primes, close quotes, primes that, not counting 2 and 3, are as close as primes can be, consecutive odd numbers like 17, 19, 29, 31. Well, no one knows. As far as anyone has looked in the sequence of primes, they seem not to, I didn't touch the screen and it just moved. Yeah, well, I guess that's it, yeah. Speaking of which, don't forget to put your clocks back an hour, Saturday night, Sunday morning, or, well, you'll be an hour early for everything if you don't. Yeah, I think that must be it. I once had a class on Halloween, and I told them that they could probably be spending the time more productively trick-or-treating instead of listening to me talk about mathematics, but, well, maybe some of them were out trick-or-treating. Anyway, so these paired primes seem to persist even as the average distribution of primes becomes rarefied. I'll say something about that in a moment. But also, I think I've mentioned at the beginning, Box conjecture. So again, a conjecture is not a wild guess. It's a sort of an educated guess. It's a guess based on something, but it's not a proof. And no one's been able to prove this one way or the other. He wrote this in a letter to, I forgot what mathematician. Anyway, he said that every even integer more than 2 is, I'll say something about y more than 2, is the sum of two primes. And the reason we leave out 2, well, actually the sum of 2, to be explicit. In fact, we proved that the sum of odd numbers is even 2 odd primes. So, I don't know, 14 is 7 plus 7. 16 is 11 plus 5, I guess. Yeah. So you can try this, but to this day, despite the enormous efforts of the greatest mathematicians, you can try it. Every time you try it, you'll find that it's true, but that doesn't make it true forever. And also, if you take a look at a list of primes, that every even integer that's more than 2 is the sum of, is the sum, thank you, is the sum of 2 odd primes. Is the sum of 2 odd primes. And the reason 2 isn't is that we don't include 1 as a prime, and in a few minutes we'll see why we don't include 1 as a prime. But every even integer greater than 2 seems to be the sum of 2 odd primes. For large numbers, in many ways, again, I didn't touch it and it moved. But the fact that it seems always to be true doesn't mean it's always true. Remember, there's an infinite number of primes, and we don't know what happens, maybe beyond any finite number that we can look at. So it's a conjecture. It's probably true, but until you have a proof, you can't assert that it is true. So yeah, the conjecture is that every even integer more than 2 is the sum of 2 odd primes. And in a list of primes, there seems always to be a prime. And when I say a prime, if there's more than 1, well, then there certainly is 1, a prime between 2 consecutive squares. So consecutive squares are the squares of consecutive numbers. But again, we don't know if that is always true. And it doesn't matter if you look at, the first billion primes, and you find that that's always true. It's still, that number is no closer to infinity than 0 is. So it doesn't prove anything. Again, it just moved without my even touching it. It's interesting to observe that this is just sort of extra. Surprisingly, if you think about this, we've talked about this a little. It's not really part of the course, but there are as many primes, and for that matter, as many squares, meaning perfect squares, squares of integers, as there are positive integers or natural numbers. Okay, I won't go into that further now, other than to say that that is a characteristic of infinite sets, that and in fact, some books will use that as a definition of an infinite set, that it can be put into one-to-one correspondence with a proper subset of itself. So a set is infinite if and only if it can be put into one-to-one correspondence, a perfect pairing, with a proper subset of itself, not the whole set. So for instance, let's look at the squares. Well, 1 squared, 2 squared, 3 squared. Okay, each one of those perfect squares can be paired with a natural number, namely 1, 2, 3, etc. N squared is paired with n. So even though the squares get further and further apart, right? So you're leaving out a lot of numbers. Well, you still have as many as you started with. Or with the primes, 2 is paired with 1. That is, 2 is the first prime. 3 is paired with 2. That's the second prime. The next prime, again, I didn't touch the screen. So 5 is paired with 3. That's the third prime. 7 is paired with 4, and so on. 11 is the fifth prime. So you see, we can count the primes, even though the primes are getting further and further apart. In fact, let me write even so, despite that fact, what's wrong with this? They are arbitrarily long. Arbitrarily long means as long as you want. You specify it, and yeah, you can do that. And I'll show you how. There are arbitrarily long stretches of consecutive, means one after another, composite numbers. Now, the primes are close together early on, 2, 3, 5, 7, they're close. But by going out far enough in the sequence of natural numbers, you can find arbitrarily long consecutive numbers that have no primes. So let's take a look at that. A few of us stayed together after Tuesday's official class and talked about some of these things, but well, again, the screen decided to move. So I'll repeat those. I'll start with a numerical example I gave Tuesday, and then I'll do it more generally. So you remember what factorial means. N factorial is the product of n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. Or if you want to do it the other way, counting upward, n factorial is 1 times 2 times 3 times dot, dot, dot times n up to n. So 5 factorial is 5 times 4 times 3 times 2 times 1. Let's look at, just to give the example I gave on Tuesday, 99 consecutive prime-free numbers. No primes, it's free of primes. Now let's see why all these numbers are not primes. Well, let's look at the first one, 100 prime plus 2. What's 100 prime? It's 1 times 2 times, etc., plus 2. So 2 is a common factor. So the first number that I've written there, 100 factorial plus 2, is not a prime because it has a common factor of 2. Look at the next one. 100 prime is 2 times 3 times, etc., plus 3. Oh, okay, so 3 is a common factor of both of those terms, and hence a factor of the whole thing. You can pull out the common factor by the distributive property, and we see that I don't recall this happening, or at least not so often, when I'm not even touching the screen. So it's not as if I'm somehow doing something wrong. The screen is just starting to move.
Professor, the screen's a little bit dirty or something like this, and it's pulling the screen to the side. You use a tablet, right?
Yeah.
So yeah, after class, you just wipe the screen. Maybe it helps.
Oh, thank you for that suggestion. That's a possibility.
Sometimes you're not able to see, but the screen is like touched somewhere, and you have like a fingerprint there that's pulling the screen. It's recognizing as a fingerprint, like as your finger.
Oh, so are you saying that if I make a mark here, well, oh, well, maybe so.
Yeah, no, it might be like invisible for the eyes. It's some dirt. You left like some fingerprint in the screen. You're not going to be able to see, but later you check it out.
Yeah, it could well be. What I do is beforehand, I do clean the camera part so that if you want to see me clearly, I don't know why you would want to, but if you do, at least the camera part is, the pickup is clean, but it's true. But what I'm saying is if I do make marks here, it doesn't seem to, I'll try that. It doesn't seem to make it move when I do make marks. Okay. And all right, I'll try cleaning it. Up to 100 factorial plus 100. Again, 100 factorial is 100 times 99 times 98. So 100 factorial has a factor of 100 plus 100 that also has a factor of 100. And so you can take it out, and the whole thing is a composite with a factor of 100. As well as other things, 2, 50, but it doesn't matter. It's not a prime. Now, notice I started with 100 factorial plus 2 rather than 100 factorial plus 1. That's because 100 factorial plus 1 may or may not be, it's certainly divisible by 3, by 1, but that doesn't make it a prime. I just have to know it's not divisible by anything bigger. And it's possible, for instance, to have, I don't think I have to write this, but notice that 3 factorial plus 1 is, so I'm trying to get composites free of prime numbers, but 3 factorial, which is 3 times 2 times 1, which is 6 plus 1, is not a composite, it's a prime. So that's why I started at the beginning here with 100 factorial plus 2 rather than 100 factorial plus 1, because it's possible for a factorial plus 1 to still be a prime, and I want to get numbers that are guaranteed not to be primes. More generally, now, I said by going out far enough in the sequence of natural numbers. I mean, these are enormous numbers. 100 factorial is, infinitely big. Of course, it's not. It's no closer to infinity than 0. But that's a tremendous number. The primes, the factorials grow very, very quickly. You may have studied that maybe in mathematics 30, 20, 30, 30, or 30, 50, where you talk about convergence of series. Factorial grows faster than the exponential function, which grows faster than a linear function. So factorials go very quickly. Those are enormous numbers, but no problem. You have a lot of numbers to deal with. As I say, 100 factorial plus 2, is small compared to what infinity would be. We can also observe that we can get arbitrarily long stretches. I gave an example with 99, but look at n factorial plus 2, n factorial plus 3, etc. N factorial plus 4, n factorial plus 5, etc. N factorial plus n. Notice that none of those is a prime number. They're all composites. N factorial, the last one, n factorial plus n, certainly has a factor of n. The fourth one I wrote has a factor of 5. So n can be as large as you want, and you get arbitrarily long stretches of prime-free numbers. Now, getting back to the distribution of primes, this had been a major puzzle, but a tremendous breakthrough on the subject was made in 1896 in what's called the prime number theorem. By Jacques Adamar. And Charles Jean actually, there's one L there. Yeah, sure, it makes sense. I don't know, prove that there's no largest prime number. That you know, every part of mathematics that has started as pure mathematics, people, I think I mentioned this before, you know, whether it's engineers or physicists, chemists, increasingly social scientists have found uses for. So, for instance, nowadays with computer applications and cryptology, you know, getting secure computer systems, the fundamental theorem of arithmetic, which I want to get to next, says that you can factor any number into prime factors. Well, if you have a 1 or 200 digit number, you're not going to be able to, even the fastest computers aren't going to be able to factor it and get the prime factors. But if you and whoever you are working with know the prime factors, no one else will be able to figure them out. So that's, you know, an example of an application of number theory to computer technology. And in order to do that, you would want to know that there's an unlimited supply of prime numbers. So that was the first theorem. But then, yeah, I don't know that what I'm about to show you, the prime number theorem has applications outside of mathematics, but just as we've been doing, even today, I mentioned, we were looking back on Tuesday's work, and we also look back on divisibility. So mathematics builds up by applying what is already known to unknown questions. And the thing is, in mathematics or in pure research, which is why it's important to, you know, support for a country or anyone to support pure research. Pure research is research for the sake of knowing something, not necessarily for applications, but so many things do unexpectedly and in unanticipatable ways lead to actual practical uses. And if you look at a book on advanced number theory, which this certainly isn't, you'll see applications to more advanced work, including, by the way, what I'm talking about right now, the prime number theorem, which depends on analysis, but a damn good grasp of analysis. It's not simple at all. So mathematics and science, and maybe social science as well, and psychology, you can't anticipate what you're going to get as the result of theoretical work. For instance, so many of the things that we use, including this tablet that I'm using here that isn't behaving too well, and GPS, you know, location devices, or mobile phones, all these depend originally on laser technology and substances that conduct electricity differentially, semiconductors, transistors, all that depends. What we have now, so much of modern technology, I mean, even a remote controller for a television depends on so many things that started as, you know, pure research. You could not have the GPS system, which, if you didn't know relativity, because in order to find exactly where something is on Earth, you have to take into account relativistic effects of the speed of a satellite, and it depends on satellites, of course, and satellites depend on, you know, what was pure mathematics. You know, the what Newton and Leibniz invented in the 1600s, calculus, is needed to compute the trajectory of an object that's thrown into the air. It's been used in warfare because they use everything they find in warfare eventually to compute the trajectory of, say, a cannonball that you're going to shoot. You have to take that into account in dropping bombs. So they land in the right place. That is their forward motion as well as the downward vector, pulling it down by gravity. As you may know, according to special relativity, when you speed something up and a satellite is going like 22,000 miles an hour, so it's moving fast enough to really have a relativistic decrease in the passage of time. But on the other hand, according to general relativity in 1915, I guess 1615, I think, maybe 16, time. Time slows down in the vicinity of a strong gravitational field. Well, if the satellite is geosynchronous, which means it's above the equator and traveling, no, I guess it's 18.5 miles a second and maybe 22,000 miles up. Anyway, it's further from the center of the Earth, so the gravitational effect is less, so time increases. So you have these two competing contradictory effects on time of a satellite, which is used for GPS. On the one hand, time is slowing down, and it turns out about twice as fast as it's increasing. Time is slowing down because of its motion, but increasing because it's further from the gravitational field of the Earth. These things are very complex. Einstein didn't anticipate GPSs when he originated these the theorems of relativity. So, and it was all, of course, based on mathematics. So, yeah, many things you learn, and not just in mathematics and science. I mean, think about your own history. I'm sure you can go back and think of things that you learned in school and earlier in school, or maybe right now in classes, which seem useless. What use can you make of them? And you know what? Education has been refined to a point based on experience where a lot of the things they teach you that you don't always see a reason for, you turn out to be useful, handy, or interesting later on. Where possible, I think teachers should make that clear. But just saying, oh, this will be useful to you later in life, that's sort of meaningless to a child and maybe almost to anyone. But you should still try to give some indication of why what you're being asked to learn is, why you're being asked to learn it. And if the teacher doesn't know why you're being asked to learn it, maybe you shouldn't be teaching it. So all these things go places. I may once have mentioned I remember specifically thinking of cosets and normal subgroups and studying them in algebra, abstract algebra, and okay, well, then I got to doctoral work in algebraic topology, and so you need that, don't you? Speaking of abstract algebra, the class I'm teaching next term is also called, in fact, it's listed as modern algebra. That terminology is used because algebra that so far goes back to antiquity. It goes, way back in different parts of the world. Abstract algebra is an abstraction of the properties, basically starting with number theory. The first thing we'll talk about is rings, which is really a generalization of the integers. And so some of what we'll do will approach in a different direction some of the things we're doing here in number theory, because it's a generalization of that. But the reason it's called modern is the origins of it really don't date back earlier than maybe the decade between about 1820 and 1830, which is very modern in the history of mathematics, which goes back to basically pre-humans who could distinguish between one thing and two things, if that's the beginning of mathematics. So the prime number theorem was developed by these two people. Apparently, La Vallée, however you pronounce it, was a single French name, but it's spelled that way. What it says, and the statement is very simple, the proof is very, very unsimple. It says that if use the Greek letter for P, for pi, for prime. And in Greek and Russian and other languages, it's actually pronounced P, but in English we call it pi. It's not really correct. So pi of n, if you let that be the number of primes less than n, then P prime is asymptotic to n over n factorial, to log n. And what that means is pi of n, the number of primes less than n, approaches n over the natural logarithm of n as n increases. So the further out you go, the closer the number of primes under wherever you go to is to that n divided by the natural logarithm of n. If you look at this in an advanced book, they won't use ln, they'll just use log, because, after elementary algebra, when you get into higher mathematics, the only logarithm you use is the natural logarithm. So they don't even bother with ln, which only started, I think, around in the mid-teens of the 1900s. It had always been log, just log, but to emphasize that it was base E, because in those days, and including in my days, in intermediate algebra in high school, we spent a lot of time learning how to use logarithms for complicated multiplication, division, powers, and roots. But now with handheld electronic calculators, we don't really do that. We're just using logarithms in calculus. So it's just written log. Anyway, I'd like to conclude today with the fundamental theorem of arithmetic, arithmetic meaning theory of numbers. And again, I'll just stick to positive integers, because negative integers, I said on Tuesday, is just -1 times a positive integer. What it says is that every integer that's more than 1 either is a prime and here's the essential part, or it can be factored into primes in exactly one way. Or as it's sometimes put, one and only one way. Except to the order in which you write them, but the primes themselves are unique. So 6 is 2 times 3 or 3 times 2, but the primes themselves are the same. The order is trivial. So I'll just put in except for the order in which they are written, but that's no difference at all. This is called unique factorization. And again, this goes to something called unique factorization domains in algebra. So this gets extended. And this theorem also explains why, I've promised you this, why we don't take 1 to be a prime. So 1 is excluded from being a prime because it wouldn't have unique factorization. It would destroy unique factorization. For instance, you could have 6 equals 2 times 3, equals 2 times 3 times 1, equals 2 times 3 times 1 times 1, and you wouldn't have unique factorization. Okay, so why is this so important? Why is it important enough to be called the fundamental theorem of number theory, of arithmetic? Building blocks, all numbers, are built from the prime numbers. And of course, the integers lead to the rational numbers, which lead to the real numbers, which lead to the complex numbers. So the prime numbers are really important. Let me just say something about the contemporaneously or concurrent but independent development of the prime number theorem. That is not unprecedented in mathematics. Leibniz and Newton developed calculus at this, more or less concurrently, one in Germany, one in England. It's not an accident. It's not so startling. All mathematicians know where mathematics stands at a particular point, and the next problems sort of suggest themselves. So it's really not so unusual. Anyway, let's prove this. Although it's past 5 after 7. Okay, suppose, say, a number greater than 1 is a composite number. Then, first theorem from Tuesday's class, it has a prime factor. Yeah, we proved what I just wrote. Yeah, we proved that. Yeah, as I said, that was it. Oh, no. So if m sub 1 is prime, you're done. N is a product of primes. If not, again, m sub 1. If it's not a prime, it's a composite, has a prime factor. So n equals p sub 1 times, instead of m, it has a prime factor, p sub 2 times m sub 2, etc. So we have a succession these m's according to the lemma that we had on Tuesday, we have m sub 1 is greater than m sub 2 is greater than m sub 3, etc. And all these are positive. So we keep on dividing, and when you divide by a number, the complementary factor is smaller when the number you're dividing by is bigger than 1, but the primes are bigger than 1. And so this can't keep going on forever. You have to finally get to an m that can't be factored further into smaller and smaller numbers. Okay, so n can be broken into factors, into prime factors, can be factored into primes in one way. And we did this on Tuesday. We took 84 equals 21 times 4. 21 wasn't a prime, so we broke it into 3 times 7 times 4. But 4 isn't a prime, so we broke it up into 3 times 7 times 2 times 2. And eventually the prime factorizations, the 3, the 7, the 2, they get smaller and smaller. That can't keep on going on forever. And so we can factor n into prime factors in one way. And now, to conclude the proof, suppose there are 2 prime factorizations of n. So suppose, say, p sub 1, p sub 2 through p sub m is one prime factorization of n. And suppose we have another one, q sub 1, q sub 2, say q sub r, where all the p's and all the q's are prime. And going back again, as we did before, to the definition of divisibility.
Dr. Friedland?
Yeah.
On that line, so since this cannot go on indefinitely, you finally get to, is that the letter M or N?
It is M.
As in Mary?
Yeah.
Thank you.
Yeah, we keep dividing. Yeah, I'm calling these, yeah, they're M's, just because I'm calling them M's, the complementary factors. And And there's no reason to suppose. I mean, maybe it's possible to factor n in two ways with the p's and the q's, but maybe it's not the same number. So suppose, say, m is more than r. Since this shows that p sub 1 divides the q's over here, this, p sub 1 divides q sub 1, q sub 2, etc., up to q sub r. If a prime divides a product of primes, it not only divides one of the primes, I'm going to ask you to review the proof of that over the weekend. It equals one of the primes. But we proved the cancellation law. So cancel the P1 and this box over here, the box. So now we're down to just P sub 2 times up to P sub m equals Q sub 2 up to Q sub r. So now this says P sub 2 it's P sub 2 times something equals the product of the q's, and that's the definition of P sub 2 divides the product of the q's, so it has to equal one of the q's, say it's Q sub 2, canceling the P sub 2 and Q sub 2, and so on. And so eventually, keep doing this. After R cancellations, so I said n is more than R. So after we've canceled each of the q's, we're left with so after that, after you've canceled R, then you're left with, on the left here, P sub, you're left with P sub R plus 1 up to P sub m. And when you've canceled all the q's, you're left with 1. So all the remaining p's 1. So, because the only divisors of 1 are numbers less than 1, there aren't any, so they must all be 1, completing the proof. That all the primes P are precisely the primes Q in some order. So for homework, recall and review the proof of the theorem that if a number divides a product, of two numbers, and it is prime to one of them, it divides the other. And prove that if a prime, on the basis of that, this is really a corollary, should be able to do it. If a prime divides a product of two primes, it not only divides it, but it equals one of those primes. And extend that result inductively to a product of any number of primes. So do that because it's what I used in the proof of the fundamental theorem above. I said that if P over here, if P sub 1, which is a prime, divides this product of primes, the Q's, then it actually equals one of them. It actually equals one of the primes. So this says this says P sub 1 divides a product of primes of R primes or N primes, whatever it is. Show that if a prime divides a product of primes, it actually equals one of the primes. And the way to do it is to go back and recall that we showed that and go back over the proof. If a number divides a product of two integers and it's prime to one of them, it divides the other. Now show that if a prime divides a product of two primes, it equals, it's not only divides, but it equals one of those primes. And then step that up inductively to show that if a prime P, this last line, divides a product of, say, N primes, it not only divides one of the primes, but it equals one of the primes. It's quite easy. You should be able to do that on the basis of the definition of primes. So we will leave it at that, and I'll come back to you. And if anyone wants to talk or ask any questions or anything else, we'll do that. And meanwhile, go over the work we did today, and happy Halloween, I suppose. Be careful with all kinds of social interaction in the upcoming holiday season, whether it's Halloween or Thanksgiving or Christmas or New Year's. We still have to be careful. I heard something on the radio that said we may be sick of the virus, but the virus isn't sick of making us sick. Was that what they said? Yeah. So, we may be tired of the virus, but the virus isn't tired of. We may be tired of the virus making us sick, but the virus isn't tired of making us sick. I guess that was it, something like that. Anyway, okay. We have to continue to be careful, and ultimately it will come to an end, as all pandemics in history have, and we're in better condition now to bring it to an end than in the past. So I'm going to get out of this and go back and speak to you.